Okay, imagine for a second that we could just snap our fingers and strip away a single, absolutely microscopic layer of oxide from a tiny piece of silicone. What would happen? Would the entire modern tech industry just cease to exist? Well, incredibly, the answer is a resounding yes. And in today's explainer, we're going to dig into exactly why that is. Let's get right into this fascinating story of how the transistor, arguably the most vital invention of the entire 20th century, evolved from a really finicky lab experiment at Bell Labs into the incredibly powerful microchips that literally run our world today.
We'll be following this amazing journey through 6 quick stages. First, the magnificent Christmas present. Then, system over magic. Third, the patent blueprint. Fourth, the Cold War catalyst. Fifth, perfecting the planar process. And finally, the birth of the microchip.
All right, starting off with Section 1, the magnificent Christmas present. It's honestly kind of crazy how fast things moved. We're talking about jumping from a super delicate point contact device in 1947 straight to a fully integrated circuit by 1960. In just a little over a decade, human history completely shifted gears.
So what did that first breakthrough actually look like? Well, theoretical physicist John Bardeen and experimental physicist Walter Brattain were tinkering with high-purity germanium. They used a little plastic wedge to press 2 gold contacts really close together on the surface. And on December 16, 1947, it worked. They modulated the current and amplified a signal up to 100 times. When they showed this off to Bell Labs officials right before the holidays, they literally dubbed it a magnificent Christmas present.
Moving on to Section 2, system over magic.
Now, you might think the transistor was just a single eureka moment by a couple of lone geniuses. But talk about office politics. William Shockley, who supervised Bardeen and Brattain, was actually pretty upset that his own preliminary work was getting overshadowed by their breakthrough. He famously complained, "Sometimes the people who do the work don't get the credit for it." Fueled by that intense rivalry, Shockley actually locked himself in a Chicago hotel room just days later and conceptualized a totally different, superior design, the junction transistor.
The big takeaway here is that Bell Labs didn't succeed by just acting like an isolated house of magic. They were the ultimate systems integrator. They pulled together decades of informal knowledge. We're talking everything from old patent specs to weird anomalies people reported in amateur radio magazines, and threw massive resources at it. Their main goal? Find a solid-state substitute for vacuum tubes. Because honestly, vacuum tubes were incredibly fragile and unreliable.
Which brings us to Section 3, the patent blueprint.
Knowing they were sitting on an unbelievable goldmine, Bell Labs went into absolute extreme secrecy mode. They stamped the whole project Bell Telephone Labs Confidential and instituted a total news blackout for over 6 months. That bought them enough time to lock down the foundational patents before they finally dropped the bombshell at a New York City press conference in June of 1948.
$25,000. Just let that number sink in for a second. That is the incredibly low licensing fee Bell Labs ultimately decided to charge for their groundbreaking patents.
See, instead of hoarding this game-changing tech, Bell Labs hosted a symposium in 1952 and licensed it to heavy hitters like IBM and Texas Instruments. But here is the best part. A tiny Japanese company called Tokyo Tsushin Kogyo scraped together that $25,000 fee. You might actually know them better by their later name, Sony. That one single, inexpensive license practically birthed the entire global consumer electronics industry, kicking off with the transistor radio.
Next up, Section 4, the Cold War catalyst.
While teenagers were listening to rock and roll on their new Sony radios, the U.S. military had a much more serious problem. They were building the Minuteman intercontinental ballistic missile, and you definitely cannot rely on fragile glass vacuum tubes in a missile guidance system. I mean, imagine a guidance computer failing just because a glass tube shattered during launch. No way. So they heavily incentivized the industry to perfect solid-state electronics, STAT. The post-war strategy basically hinged on superior tech to offset the Soviet Union's numerical advantages. Through defense contracting, companies like Fairchild Semiconductor had to adopt flexible specialization, building custom, ultra-reliable chips to meet wild military standards. Essentially, the Minuteman program wrote the checks that funded the crucial research into making these components incredibly reliable and mind-bogglingly small.
And that intense demand for reliability leads perfectly into Section 5, perfecting the planar process.
Down at the microscopic level,
engineers were furiously experimenting to build better structures. They were testing out early diffused-based devices, swapping around elements like aluminum and gold on silicon, just trying to figure out how to mass-produce these tiny amplifying wonders without them leaking current or shorting out.
And during all that messy experimentation in 1955, researchers Carl Frosch and Lincoln Derrick stumbled onto something huge. They realized that a specific layer of silicon dioxide naturally formed and protected the silicon, stopping leaks and allowing for ultra-precise oxide masking and patterning. Remember that question we started with? Without this exact microscopic protective layer, today's semiconductor industry simply wouldn't exist. It is the absolute bedrock of modern electronics. Finally, we reach the culmination of all this genius in Section 6, Birth of the Microchip.
You know, you often hear Jack Kilby and Robert Noyce debated as the co-inventors of the microchip, but their methods were literally night and day. Kilby built a hybrid device out of germanium, and he connected his components with thin metal wires literally just dangling above the chip. Noyce, though, he looked at that beautiful silicon dioxide planar process we just talked about and realized he could interconnect the transistors by depositing flat aluminum wires directly on top of the protective oxide layer.
By interconnecting everything flat right on the wafer, Noyce and the Fairchild team, building on Gene Horney's vital planar process, created the true monolithic integrated circuit in 1960. The key thing to remember here is that Noyce's monolithic design is the only kind of microchip that has ever been manufactured and sold since this industry started. It's that incredibly elegant, scalable design that lets us pack billions of transistors onto a chip the size of your fingernail today.
So we'll leave you with this. Next time you pull out your smartphone, just ask yourself, where would we be if Bell Labs had kept those patents totally locked in a vault instead of letting them go for 25 grand? Or what if the extreme pressure of Cold War military funding hadn't forced the rapid perfection of the silicon chip? It truly took a perfect storm of collaborative science, massive military necessity, and surprisingly generous strategic licensing to build the digital world we all live in. Thanks so much for hanging out for this explainer, and we'll see you next time.